official contest. Let's do it after the speaker. What the thought is we have our 6 to 7 are social, 7 to 8 are speaker. 8 o'clock on is basically just people milling around, chatting, looking at projects, show and tell. Be a good time to be running that over the wall over there. Sometimes people do a show and tell their own projects here. It kind of both people can go where they want to go, and they can hang around for another hour or so doing that. That prevents us from having to delay our speaker. Now we've only got a couple tonight. Right here. Oh, is that which one is this one from tonight? Oh, very nice. Okay, we have one. So who's got the sign-up sheets going around? Let's do this. Once you stop and pass the official one around. Thank you very much.
It doesn't matter which one you use. I just printed it because I was looking at it.
A little bit of background, basically. Normally I'm more organized than tonight. But let's say I took the day off today from work. I didn't feel too good. Doctor says I'm not sick. I went to see the doctor today. He says I'm all right. I disagree with them.
It's just a virus.
I disagree with them. I'm keeping distance from everyone tonight, and I've been kind of disjointed and disorganized tonight, so I didn't have that printed off. Thank you for getting that done for us tonight. I'm going to start with initial introductions, where our speakers getting ready. First, welcome to the IEEE Robotics and East North Carolina Robotics and Automation Society. For those that actually have been involved in the robotics in the area for a long time, Ken Boone basically been one of the long timers in the front. We used to meet as also Triumph Robotics Club. TAR is actually one of the oldest amateur robotics clubs in the nation. When we first were putting a list of robotics clubs in the early mid-'80s, there was like 10 clubs in all the United States, and we were one of those two. Actually, probably one of the first 3 or 4 clubs in the nation. Over the years, we've been meeting on state campus for a long period of time. We met basically through originally at the textiles building, the fine engineering building, and we had our official election in 1998. I think it's going really well. The tech shop died, unfortunately. At the same time, robotics and automation have been meeting for a very long time as well. Also, a very big organization, way bigger than TAR by far, locally as well as internationally. But they were actually looking for some new people to help them. So it was a perfect time to combine a hobby group, a TAR, and a professional group of IEEE together under one roof. We got the energy, we got the people, we got the resources. That's where our goal is going forward. So basically right now we are IEEE Robotics and Automation, small subscript Triumph Robotics Club. I can't drop that one for a while, even though IEEE may not like that, but it's basically still basically there. My name is Rodney Radford. For those that probably everyone here knows me. Starting this month, I'll be leading the IEEE Robotics and Automation meeting here for this year. I'll be looking for some volunteers for next year. So once you come see me walking towards you, don't run away. We also got Grace Lee, our lead for 14 years now. Basically stepping down as chair this month. But I still drug him in as vice chair, because I needed his expertise to help me going forward and go through with all the various getting the room together and getting people together, etc. So he's sticking on helping us going forward as vice chair. First, who was here last month? Who liked last month? We had basically a joint meeting, IEEE, TAR, and Tri-Embed. You got the book.
Yeah, I got the book.
Mine's not here yet.
I got the book.
Yeah, I got it. They have it also. It showed up just the other day.
Mine's, for different reasons, not here yet, but I haven't seen one in print yet, so I want to see one in print. We had a great meeting last month. It was energized, had a lot of fun. Looking for more of those going forward this year. We got a good meeting next month as well. Kristen Vidal, who's been coming here for probably 2 years in a robotics club. She's a teacher, I think the school. She's Evelyn Cheeks Elementary. And basically, it's a fairly poor community, basically. She says over half the students in there are below the poverty line. And she's been bringing forth some really good science programs, robotics programs into that sort of school. A lot of challenges, and a lot of good success. She was talking about her project next semester and showing us the things they're doing. Actually, they just got a 3D printer recently, working on that. They've got a couple of Lego projects working on, and a lot of good. So they should be presenting next month. It'll be another really good meeting. Still looking forward to bringing in March and April meetings, announcing those pretty soon. Expect a lot of more good meetings coming forward. Before I introduce our speaker, which hopefully no one needs to introduce, I need to introduce two other people first. Ken, people say in the back of my head, wave hi. He's been at a lot of the meetings. I met him through IEEE just recently here, but he's actually the section chair for Eastern North Carolina section chair.
That's it.
And sitting in front of him basically is Mary Ellen, who's our speaker's wife, and she's the Region 3 director starting this year, which is a very, very big role. All of Region 3, which is basically how many members of Region 3? So I know it's big. It's
like 27,000 members or something, all the southeast U.S. and Jamaica.
That's a huge area. Basically, the IEEE Region 3 Southeast Con is showing up in March.
In Lexington, Kentucky.
Yeah, so I'm still hoping I can go to that. I'm hoping to find some way finagling to get to there. It's still work. If you let me off the time, I'll pay for the trip. So it's a pretty good deal. Hopefully I can go to that one. But they're here tonight, and actually they're here a lot of nights. Stop by and say hello to them. Now, everything ready? Okay. Our speaker tonight is Grayson Randall. Hopefully everyone has seen him before and knows who he is. But a little background. 12 years IEEE Robotics and Automation chair of that. He's vice chair this year. He's also head of InsideRacing.com. He won the Outstanding Engineer Award for IEEE Region 3 in 2009, and also received 2007 an award for leadership for pre-college and college students getting interested in robotics. He was also led the DARPA Challenge 1 and 2. The second one went through state campus. I remember watching the first one. What was that car you had? It was the truck.
Suburban.
Suburban. I've never seen the Suburban low-tech solutions you've ever seen actually doing really well, navigating through this field basically. Amazing watching. I didn't watch to see what Stanford and other communities are doing. Amazing dollars they're spending. Watching the few dollars they're spending here was amazing, the results of that. So next year, the second year, actually Lotus got involved and actually donated or loaned a car for them for the second year. She's been discussing, and also discussing a project he's hoping to go forward with this club and with this group and other groups. This is the Lifeline Humanoid Robot. So with nothing more, I'll sit down and walk to the floor. Thank you very much. And when he finishes, we'll be doing the show and tells around the floor and robotics competition over there.
My clicker's not working.
So I'll be the
We're gonna do the clicker tonight. Thank you very much, Rodney, and I'm glad everybody came. I understand I'm up against the BCS Bowl tonight, so it's good to see everybody here. We started the DARPA Grand Challenge in like 2003. And it turns out that the section, the IEEE section, actually funded me to go out to California to the kickoff, which really started off this whirlwind 7-year event that took my whole life away for about 7 years. But it was a wonderful event. I would do it again in a heartbeat. It was very exciting. So essentially, there were 3 events. The first event in 2003, there was, I forget the numbers now, it's ancient history, but there was only like 25 entries. We actually were invited. We actually passed all the tests and went through the process and was in one of the teams that was invited. But being a young team, we basically had no money. So I took the gamble that no one would win the contest that year because DARPA said that if there's no winners, then we'll do it again. So I gambled, and out of the 120-mile course, the furthest anybody got was 7 miles, and that was Carnegie Mellon. And the press went berserk. They said, "Oh, this event was a failure. DARPA put all this money in. Nobody was able to do it." The reality is that we only had about less than 18 months to put the teams together, to put the funding together, to design the vehicles and prepare for that. And even teams like Carnegie Mellon and Stanford and whoever didn't really have time to get the project really rolling. So there was a second event, the 2005 Grand Challenge, 130 miles through the desert. Basically, it was a desert course, and essentially you had to be able to drive the 130 miles with no driver and no remote control. The vehicle had to be fully autonomous and self-operating. So one of the trials that we had to do, this is actually pictures from the event where DARPA, it was the preliminary before the finals. It's like the semifinals of the event. It was a very long process. You had to sign up. Then the initial one is you had to send them a 5-minute video to show them that you actually had something and that it actually moved and did something. Then if you passed that checkpoint, the next checkpoint was an on-site visit. And DARPA actually sent a team of people to each site, and you had to have a course set up. And they actually set up a series of tests where they actually put things in the road and did a variety of different things, and you had to pass, and they scored you on all the tests. And if you did well there, those teams were invited to California to the semifinals, where they did a very big, elaborate test setup there. And then the teams were selected from there to go to the finals and actually go out into the desert and to do the desert course. So this is the semifinals. It's actually a speedway, a giant speedway in California. And what happens is that we pull the vehicle into the start gate. DARPA would walk up with a thumb drive and pass it to us. And it basically had the checkpoints on the course that we had to hit. Basically, it was a description of the course. We had 5 minutes to load the course in. So essentially, we didn't know what the course was that we were running. So we loaded the course into the vehicle. We put it in autonomous mode and switched it over to their control. And they had a sophisticated remote e-stop box. And essentially, we were required to wire in the other end into our vehicle. And there were basically 3 modes. There was pause, there was run, and then there was e-stop. And e-stop, essentially, you were required to shut the electrical down, the power down. And once they hit e-stop, there was no way to restart the vehicle. So if DARPA felt that your vehicle was unsafe and hits e-stop, you were done. Now, there were conditions where they would put it in pause because there was something on the track or people weren't in the right place, and they would pause it and then allow it to continue, and that was valid too. So we would pull into the gate, they'd give us the course, we'd load it, we'd put it into pause mode, they'd take control, and then we would leave the area. And when they were ready, they had a team that followed in a pickup truck, and they basically followed the vehicle and they hit run, and it would just go through the course. So here was the first gate. We actually came in at an angle, so it wasn't straight. You had to come in and swing into this gate. But there were a lot of vehicles that had trouble getting through the first gate, so that was always good. Next. Then we went down and we came back, and they actually built this tunnel. and they put aluminum over the top to prove that you could drive without GPS signals. So you had to, once you entered the tunnel, you had to be able to use other means other than GPS signals in order to navigate the vehicle. And then once you popped out, you could reacquire and pick back up on the course. This one looks very simple, but was actually very challenging because it's a stack of tires, which doesn't look like a big deal. But a lot of the vehicles right here, you actually had to get very close to the tires before you could swing and stay within the cones or the lane. So you had to pull right up almost to the tires in order to swing through and exit that checkpoint. Okay? There were a number of vehicles on the course, and of course they were right in the middle of the lane. And there were quite a number of vehicles that hit them. So luckily we were able to maneuver around this one.
Did that cause an e-stop? If you could?
Yes, yeah. E-stop was, if you hit stop, then you were done. So
How many teams were there the second time around?
the second time there were 189 teams that applied, and then they kept getting weeded out through the process, and there was actually about 20 teams that participated in the final event. So, and then from there, we actually headed out into the desert to run. So,
Yeah, this was the finals.
yeah, that was actually, this is actually the finals. And the vehicle was headed out through the course.
Some of them went up through those Jersey barriers, right?
Yeah, one team hit the barriers, and so,
We were standing there too, to run.
yeah. So that's Stanford. And of course, everybody knew that Stanford and Carnegie Mellon were like head-to-head and challenging each other. And Carnegie Mellon had a very interesting approach because they basically pre-mapped the course, and they knew where the vehicle was supposed to be, what speed it was supposed to be, and they had it laid out foot for foot, the entire course. It turns out that in the middle of the race, they developed engine trouble, and the vehicle didn't perform correctly. They actually had difficulty getting up some of the hills and stuff, and it threw their timing way off. And Stanford actually won that first event in 2005. You can see that's the DARPA vehicle that was following them through the course.
So, Grayson, what criteria were used for winning? What obviously timing was part of it. What else?
Timing and finishing. Yeah, there were actually 5 teams that finished the second race. This is after the first race where nobody got. They only got like 7 miles. There were actually 5 teams that completed the course in the second one. Now we actually made it to the finals, and we actually placed 12th, well actually 11th, depends on which chart you look at. But we placed 11th, and we would have done better, and I know everybody says that, but early in the race we had a 3-axis gyro that failed, and essentially the vehicle didn't know or couldn't track direction, and so it basically it wandered. We drove the 130 miles, but we only got about 40 miles in distance. But it wandered back and forth, and eventually ended up, because we were late in the afternoon, the sun came in the front, blinded some of the equipment.
This kind of shows some of the high tension.
Yeah,
Stuff.
some of the high tension. Okay? So, So that's a quick through the first race and through the second race. So we came back after the first race, and theoretically, that was it. DARPA said once there was a winner, that would be it. And then a few months later, DARPA came back and said, well, we're doing so good, we want to have another one. So we had another 18-month cycle to do the urban challenge. So this time, instead of driving through the desert and avoiding rocks and cacti, we actually had to drive on city streets. We actually had to obey intersection rules. We had to be able to do traffic circles and interact with other vehicles. So there were other traffic. There was not only autonomous traffic, but in the finals, DARPA actually had manually driven cars on the course with the autonomous vehicles as well. So now we're going to have to do another round. After our finish in the second race, we actually got connected with a person from Lotus, and this is the Lotus Sports Car Company. They have a Lotus USA is in Ann Arbor, Michigan, and they actually have a factory up there. It's not a production factory, but they have a facility there. And we had the opportunity to talk to some people there that really wanted to participate but didn't have the software skills. And we had the software skills, but we were driving the old Suburban, and so they offered us a Lotus Elise. And we still joke about it because the first thing I said was, it's awfully small. Because we had like a computer rack in the back of the Suburban to hold the computing equipment. And the urban challenge was much, much more difficult. In the Grand Challenge, we basically only looked forward. We were basically scanning the ground to look for contours of the ground. And we were scanning horizontally, looking for objects so that we could avoid hitting objects. When you get to the urban challenge, now you've got to know what's in front of you, what's behind you. You got to be able to recognize, a lot of stuff that's going on. And it's a much more difficult problem than the urban challenge. So we had to take all the equipment we needed and get it into a trunk that we couldn't even get a set of golf clubs into. And it was, and you'll notice I have some pictures of the other teams, and they're all driving Suburbans and stuff. So it was quite a challenge. Yep.
Yes, were you using LiDAR for your point cloud scanning?
Yep, we'll talk about that, but we had LiDARs, we had radar, we had cameras as the main sensing.
Okay.
Grace,
Yes.
how much did it cost to get through the first cycle with the?
We spent about $50,000 on the first cycle, and close to that on the second cycle. So
A lot of equipment was donated.
Yeah, we got tons of equipment donated, and of course all the time was donated and stuff. So
And can you compare that to like Stanford and those teams?
yeah, nobody was required to give out their financials, but it was rumored that Carnegie Mellon spent close to $5 million on their project, and Stanford was less than that. Actually, Stanford was very impressive. They had a fairly small team, and they were funded through Volkswagen.
Mhm.
Yeah.
Mhm.
So they had money coming in to support them from the car manufacturers as well. And just Carnegie Mellon is tied in directly with GM, so GM was supporting Carnegie Mellon in their work as well. But yeah, there was quite a contrast between the top and the bottom. So.
One thing of interest is that one of the participants that I think finished the second race is now, that same vehicle is an approved military vehicle. It's
Yep.
the Max, what was it? The Terramax.
Terramax.
Yeah.
And I got a picture of Terramax, so
Yeah.
so we'll see that. But yeah, it's pretty impressive. So Lotus agreed to give us a lease, and we did work out a deal. Once I talked to the team, everybody goes, "We'll figure it out, don't worry." So get the car, we'll figure out how to get the stuff into it. So we basically broke the project into 3 major groups. Lotus did the vehicle and made some major modifications to it to support us. I had the software development team and the kind of the overall project management. And then NC State did all the mechanical and electrical. They mounted all the hardware, they pulled all the cables, they did all the setup and adjustment of the equipment on the car. So that's kind of how the teams work together. So we actually spec'd it out for Lotus, and Lotus took the car to Ann Arbor, and we actually tore the car apart. The first thing is they mounted a motor on the dash, and the motor is connected to a drive belt on the steering wheel. And that allowed the vehicle to be steered. We actually just tied right into the steering wheel and manipulated that. And if you turned the power off to the motor, you could drive it. It was a little stiff, but we actually used to drive it out on the highway and take it out for gas and stuff and bring it back. So it was road drivable, even though it had all the autonomous equipment on it.
It was required that it had to be drivable by
Is that-
hand as
By
well
hand,
as
yeah.
autonomous.
Is that because Lotus actually only has a non-digital steering to begin with? They have like a hydraulic-based power steering and a whole bit, versus some of your modern cars that actually have, you know, stress sensors and electronics?
Yeah. That's the way we had done it previously, and they decided that that was the easiest way for them to do it, so they did that. There's a large actuator on the floor that actually pressed the brake. We actually worked with them to electronically brake it, and even Lotus said there were so many interlocks in the system that they couldn't figure out how to do it electronically. They said, we're just going to push the brake pedal, and that's the way to do it, because of all the safety interlocks that were in the electronic braking system.
And we didn't have a lot of time either. It was.
Yeah, we were in a rush. Next.
Did any other teams use any of the drive-by-wire, the CAN bus to basically do braking, acceleration, and steering?
I think a couple of them did, not a lot, but I think there was some that was
Did they
able
get
to do
approval
that.
from
But
the
you really have to be tied into the manufacturers in order to get access to that stuff. Even Lotus modified the CAN bus to give us information about the engine, and we used the CAN bus to signal them on some things that we wanted to do as well. They cut the back off of because the trunk entrance was so small that it wasn't workable. So they actually cut the back of the car off to give access to work. Go next. You can see we mounted additional batteries because we were totally self-contained. So we actually had to power all the computer systems, all the sensor systems, plus the vehicle systems from onboard power. So they put a larger alternator on, and then we actually used it to charge the DC battery packs in the back. And then we ran the equipment off DC. So all of our sensor systems and computers are all direct off the DC power. This Lotus is the only Lotus in the world with an automatic transmission. Everybody goes, how'd you do that? And they actually took out the 6-speed and they actually put in an automatic transmission out of a matrix, I think. And they actually fit it in. And then this equipment here is actually the actuator for driving the shift control on the automatic transmission.
Did Lotus do that, or did NC State do that?
Lotus did that. The actual, the vehicle automation was done by Lotus. Then they gave us an interface to code to so that we could manipulate it. And actually, this was actually wired to a switch on the dash, and the dash was park, drive, autonomous. And so you could flip it to drive, and then you could drive the car and drive it out on the road. And then when you get ready to go to autonomous mode, we just flip the switch to autonomous. This is a film crew from Discovery Channel. Discovery actually followed us and did quite a lot of documentation on our team. And the facility here is called a rolling highway. It's a dynamometer for those that are familiar. The car is actually sitting on a giant, the back wheels are sitting on a giant roller that they can hydraulically control to make it look like we're going uphill and downhill and stuff. So we actually went to Ann Arbor in January. It was about 20 below zero there. But we actually set the car up on the dynamometer. We loaded our first pass of software on, and Lotus actually had the first pass of the hardware. And this was the first time that we'd actually integrated and powered them up. And we actually were able to start the car, shift it into gear, and bring it up to speed while we were parked inside the facility. So.
We ran along our simulated road, too.
Yep, we had a simulated road, and Discovery Channel was there taking pictures. And
Did you make the cutting room floor or not?
did
Did
what?
you make it beyond the cutting room floor, or did you actually make the show about?
Is there a discovery program out there on this?
Yeah, we were on a couple of segments.
Twice. They sent a film crew from England, too, that came.
I've also got pictures, the BBC, well, we'll talk about it when I get there. So you can see the roller here under the tires, and the car's actually strapped down. They actually run straps and strap it down. Then we're able to start it up and electronically through the software, start the car, put it in gear, and actually drive it.
Was this Lotus's facility, or was this somebody else's?
This is Lotus's facility in Ann Arbor, Michigan.
It's a cool car.
So once we finished the integration phase there, and the car was essentially, we had the interfaces to work with, we actually brought the car back to NC State. And the car was actually stored in the solar building. They have a small garage in the back, and we actually kept it there. Next meeting. So I don't know if you're familiar, the main building's up here, and then in the back there's a building. The trailer was also donated to us for the duration of this 18 months. And we're actually able to put the Lotus in the trailer with all the sensors and stuff and transport it. And the trailer has been all over. We went to Michigan, we went to California. We did a lot of testing at the airport in Kinston, which is about 2 hours, hour and a half east of here. And we used to go out every Friday night and test Friday night, all day Saturday, and then come back Saturday afternoon to Raleigh. So the car was in and out of the trailer all the time. And pictures of, initially, Lotus had a double of a time setting up. We needed the framework up front to mount all our lasers and our LiDARs on. And there is very little structural material in the front of a Lotus. So they actually had to go like way back to the firewall to get a place where they could actually latch on. And then they brought all the framework forward for us to mount all our equipment on. Next. Now this is the airport out in Sanford. We did some initial testing out there. We liked airports. Airports were, A, there was nobody around, they were fairly secure, and B, they were, you know, it's a lot of space for us to work in. This audience is pretty familiar with development projects and how it goes. For those people that think that you just create something and it looks really nice, you know, this is how you start, you know. We had wires and we were stuff hanging out, and we were trying to locate what equipment we needed, where we were going to put it, what's the visibility of the cameras and stuff. Next screen. You can see we had a tripod strapped on the front with a camera. Because the Lotus was so low, we needed to get the camera up so that we could see what we were doing, but there wasn't a lot of places to mount them. So we did a lot of testing, just driving around trying to get the camera views, get the LiDAR views, and figure out where we were going to mount all the equipment. Yeah, spaghetti. So let's move on. So let's go back. This is a radar unit out of I think a Cadillac. This is a 3-axis gyro. It allowed us to see our attitude, whether we're going uphill or downhill, what direction we were going. We had 2 GPS systems. We had a military-grade GPS with fully equipped up top. We had e-stops, you know, located around the vehicle for emergencies, and then the batteries and stuff in the back. Of course, it's a mid-engine if you're not familiar, so the engine was sitting right here in front of the trunk space.
Heating up all our equipment.
Yeah. And for those who might ask, what was the most difficult part of this project? And I never would have guessed this when I started this project. Heat management. Managing the heat turned out to be the death of me. We had so much trouble managing the heat.
Was that true with the Suburban as well, or was it just with the Lotus?
No, the Suburban was fine. When we bought it, it was primer gray, and it got hot. We had it painted white, and it cooled the temperature like 20, 30 degrees in the car by painting it white. And it had an air conditioning, and it was enough to keep the interior fairly respectable. This one has an air conditioner, but they might as well have had a fan, you know, because it virtually did nothing. And originally we tried to duct air into the back, and that didn't work. And after months of trying things, we eventually mounted an air conditioner under the vehicle and actually blew the air up into the trunk area. But of course, Now you're doing power management, because when you start running air conditioners, you're really drawing a lot of power. So you're trying to balance the heat problem with the power draw, and trying to make all those components come together.
Guess a long pause would kill you.
What'd you do, get a ticket?
Well, who gets the ticket when nobody's driving?
The guy on this side.
Now, these were taken, 7 or 8 years ago now. And even then, I always told in my talks that the problem wasn't the technology, the problem was the legal system. Now, currently there's 4 states that allow autonomous vehicles on the road. And we'll probably see more in the future. But this particular case, we used to drive on the NC State campus a lot. And every weekend, campus security would stop and say, "What are you doing? You can't be here, da-da-da-da." We'd show them the car, and we'd tell them all the great stuff, and they'd get back in their vehicle and leave, and it wouldn't bother us for the rest of the weekend. They were always very interested. But it is a big problem. The legal issue of not having a driver in the vehicle is very difficult. And it drives a lot of the technology. Because even today, we have most of the sensing systems available on production version cars. But it all feeds back to the driver, some indicator or some light. And until recently, when like Volvo has their city system, whatever they call it, it actually stops the vehicle if it's going to hit something, So they're starting to get into that, but it's been a very difficult path for them, particularly from a legal aspect.
What 4 states? Montana,
Nevada.
Nevada, or
California.
Florida, Michigan.
And is it Massachusetts? I know there's one out east.
Is there? Michigan just signed a few weeks ago. So.
Good thing we didn't know you couldn't have them in
I
here.
thought there was one on the eastern seaboard, but I can't remember. I thought it was Massachusetts.
Yeah, I don't know. So here's a picture of driving. We always had a safety person in the car. You'll see, when you see some of the pictures, normally you'll see somebody there. Their role is basically just to ride along and hit the e-stop if required. And we almost never, I can't think of an instance. I can think of one instance. Yeah, we jumped the curb, but in general, it wasn't a problem. And the rider, one day something funny happened, and we always had walkie-talkies, and we called the driver, and he said, what just happened in the vehicle? And there was nothing, and we called 2 or 3 times. He goes, "Oh, I'm sorry, I was on my cell phone." So the people that rode in the car very quickly become very complacent about being in it and riding. Everybody's like, "Oh, I don't know if I want the car driving." And once you've done it, it's very, very easy to get comfortable with it.
Google and all their research out in California found that it was almost immediate.
Yeah. We found the same thing. Any fear of riding in the car went away almost instantly once they got in. And it was next. Michio Kaku, I don't know. He's on Fox News sometimes.
World known physicist.
Yeah, world physicist out of,
Yeah.
I think, MIT.
Yeah.
He was doing a show called The Future.
Yeah.
And they were doing segments on different technologies that were going to happen in the future. Well, they actually selected our vehicle to do as the automotive future. And we actually brought him in and the film crew and spent a day with him filming. And we put him in the car, and we drove the car a mile down the road. And they ran the film crew in the pickup truck beside him. and they filmed his lines as he was driving down the road, and he was talking to the camera with his hands and stuff, obviously not driving the vehicles. So it was pretty cool. It was a lot of fun.
I just read his last
I
book.
saw that.
Yeah,
Oh, did you?
Yeah, he described his way to stay with you guys in there.
Oh, really? I haven't seen that. I'll have to check that
What
out.
was it?
His last book, it was like the next,
Oh, yeah?
you know, Life in 2100 or
Oh, cool.
something. But,
Says we're in there.
So we better get it.
Yeah. So another shot of the interior. We did have a display primarily for the operator that was riding. He could see the course was laid out on the screen. He could see where the car was in relation to the course, and he could also see what the sensors were seeing. So it was kind of a ride-along, gives the operator something to see.
According to the internet, and I don't see the source right offhand, it says there's 4 states that have legalized it as of the end of 2014. Nevada, Florida, California, and Utah.
Yeah, that's what I thought.
What about the acceleration logic? Was there a sense of the speed limit in the urban area?
I'm not sure. I
Speed limit.
The speed limit.
As part of the input file, the speed for each segment was included as part of the data. So when we got the thumb drive, the magic thumb drive, it would tell us what the maximum speeds were for each segment. So we could drive to that.
Did you have to visually see stop signs, or was that part of the file?
No, that was part of the file, actually. You didn't have to visually see them.
How did you determine the speed at which you traveled? Would you go right to the max? Probably not. Based upon obstructions and the terrain in front of you, you would have to make a decision. So how was that decision made?
That decision was a combination of a bunch of inputs. But essentially, we evaluated the course, the objects within our view, and attempted to calculate trajectories of objects in our view. And we would attempt to adjust the speed. The speed was also adjusted based on vibration in the vehicle. If the road started getting rough, we'd back the speed down. So we also use some vibration analysis to help adjust the speeds as well.
So how much CPU horsepower did it take for all those?
We had 8 dual-core Mac Minis on board to do the calculations and the processing. And then we had another probably dozen, they weren't Adrenos then, but it's essentially the same, small processors that we used to drive certain pieces of equipment, to move or articulate certain pieces of equipment. So we had the 8 dual-core processors running the hardcore stuff. And that was set up on 3 Ethernet subnets. Because of the amount of data coming from all the laser scanners, we had to break them up on multiple subnets in order to manage all the Ethernet traffic on board as well. The other thing that we did is a lot of the sensors were all serial interfaces. So we have these boxes here that are serial to Ethernet converter boxes, so that any processor can pick up and read any serial line without physically moving the cables. So we had failover capability. Certain processors could fail. The other processor would actually grab the readings and pick up and continue without having to rewire any of the serial interfaces in the vehicle. So.
Did DARPA ever require you to disclose any details of your architecture?
Yeah, we had to do a report, but it wasn't terribly detailed. You know, so.
So even the winner had no obligation
Right.
to DARPA?
Yeah. But there was a bunch of contractual stuff that essentially, if DARPA wanted it, DARPA got it. You know, it was kind of hard to work around that stuff. So, but I don't think they exercised that. Even like Terramax, what they did is they ended up funding the companies that they thought had potential to work there, to be helpful to the technologies they wanted. So DARPA's a research group, and they're not even a research group, they're a grant organization. So basically, they are funding organizations to do stuff and to track stuff, and so they really don't have a need for that, other than to know what it is and what pieces of it that they want.
As a contest, they usually put right in the contract that there is no implied or explicit promise of a contract coming out of winning or even placing in that contest.
Yeah. They don't guarantee it, but they have that option. And in this case, it wasn't the winner. Terramax didn't even finish, and they got the contract. So, you know, it was up to whatever discretion that they wanted to do.
It finished the second day.
Yeah, I think it did.
It did finish.
The last.
I thought it ran into...
Yeah, and the third one it didn't, I think, and the second one it finished, the desert one it finished.
The second one it finished.
Yeah.
The second.
Yeah,
It was
okay.
the
It
third
actually
one.
they had to go restart it.
They
because-
sat overnight and they
Yeah.
had to
Yeah.
refuel it in the
Yeah.
morning
Yeah.
and stuff.
We
Yeah.
were the only other vehicle that was in consideration for shutting it down overnight and restarting it. Yeah.
Trying to remember what it's going to say. Drats. Oh well, that comes with age.
They'll come back. So we had 2 GPSs on board. The one GPS had what's it called? Yeah, an INS. So you had an INS on the one, and so it's a military grade INS. So we could actually operate up to 30 minutes without a GPS signal and still know where we were. So we could track the ground and stuff using the inertial nav.
They had an inertial system built in?
Yeah.
Okay.
That
Yeah,
was based
inertial
on active
navigation.
gyros.
What?
That was based as long as your gyros were working.
Yeah.
That your INS would work.
Yeah.
Well, we
We had
that
2
gyro,
sets.
Yeah.
We had our own set, and then the GPS had a
Yeah,
special
internal set, okay.
that was donated to us.
I worked on
And they
a-
hunted us down and got it back.
I worked on a DARPA-funded project, and at the end of the project, we had to return not only the hardware we had generated, but like crimp tools for the connectors we had to return.
Yeah,
So it's in some warehouse somewhere that nobody could ever use.
yeah, I'm sure they want everything back
Yeah.
that they paid for.
Well, we weren't DARPA funded.
Yeah, yeah. The contest, just so everybody knows, the second contest, there was no funding. All the teams were self-funded. So the DARPA expense was to put the event on and to do stuff. They did not fund any teams. The Urban Challenge, DARPA actually funded 5 teams, and that was a disaster. They won't ever say it, but
Some of them didn't make it into the finals.
yeah, and some of the teams that did really well didn't, and all their teams got in, and so there was a lot of hard feelings about having some teams funded and a lot of teams that weren't funded.
What they're doing in their current set of contests is if your team makes it to whatever set of challenge hoops they put in as participating in the contest, they will pay for your travel expenses, but they won't be paying for any of whatever it takes you to, or whatever expenses you may have in participating. You're on the hook for that on your own.
Yeah.
And this is only there for testing so that we
Yeah.
can watch what's going
Yeah.
on.
We used to follow in the chase vehicle. We all had our laptops up and we were all connected to the Wi-Fi, and we could monitor all the systems and watch what was going on. And if something went wrong, we'd stop the vehicles because it was virtually impossible to reproduce a failure. There were so many inputs, so much stuff going on. To set the test up again, it would never fail the same way. So, one, we had a tremendous amount of logging going on. We logged everything. And if there was a problem, we would stop and we'd all go through the logs and we'd compare data and all talk about it. We'd make a couple of changes. We could download them from the chase vehicle into the car, and then we'd restart and we'd continue and we'd go from there. But to try to set up, the vehicle was never in the same position. The dynamics of getting there wasn't there. The sun would change, the GPS would shift around, and so we had to capture failures on the fly, stop, try to analyze them and fix them, and then we'd move on.
We could simulate from the log stuff. We could at least run it through a
Yeah.
simulator.
But it was still difficult.
Yeah.
We did most of it on the fly.
What do you mean by failure? I mean, did you hit something?
Not necessarily. I mean, if I expected the car to go to the left side and it goes to the right side, it's like, whoa, why did it do that? It shouldn't. In my mind, based on the inputs and the data flowing, that shouldn't have occurred. Let's stop and figure out
What happened?
what data was bad, what caused it to do something that was unexpected. I guess that's what I would call a failure. Because the car did do unusual things. And in one of the trials with DARPA, and we were out in the big course, we were watching, and there was a car in the road, and it was like to one side of the center line. And our car come tooling up behind it, and it clearly had tons of space on the left side, and it went to the right, and I was like panic-stricken, because I didn't think it had room to get through. But it did, and I don't know why it selected the right over the left, but it calculated it had enough space, and it went through.
It was shorter, right?
Yeah, and it went zoop through and kept going. So we couldn't always predict what it was going to do. You just wanted it to try to do the correct thing. So, next.
The most.
So, this is our facility in Kinston. The airport made us available to us. Basically, it's a shipping bay. It's where they unload the planes into here, and then the far end there's a dock where they can back the trucks up and load them and stuff. But we used to spend our weekends here making changes and testing.
Now, Kinston, is that like the global transport? Or
Yeah,
whatever
It is,
it is?
absolutely,
Yeah.
yep. And
This is it, the global.
this is some of the facilities. This is a taxiway, actually, and we used it for driving. We also, this was a part of the airport that wasn't being used. Had been, when they put the big runway in, this was left over. We actually, NC State loaned us the line painting equipment. We actually went out and painted the roadway onto this taxiway. And we had to have a four-way intersection, and this one actually loops around and comes into this side. This one goes out and goes back. We were actually in right about here on the other side of this building is where the other pictures were. And then this road to the right actually goes out and stops. It was a dead end. So the car went out. It had to make a K-turn, turn itself around in order to come back and stay on the
And that was
course.
one of the hard parts, was finding something we could configure the way DARPA wanted it
Yeah.
for the site
Needed
visit.
a lot of space in order
So
to
that
set up
was-
this course for DARPA. Next. We talked about heat. the day DARPA came to do our site review, which was a really big deal, because it was our ticket to California. It was the hottest day that we had operated. It was over 100 degrees in Kinston. Absolutely terrible hot. We drove through we had like a 4-hour window to complete the testing. And about halfway through, in fact, we were doing excellent. We were like killing it. We were just doing everything. About halfway through, the vehicle stopped. I mean, just came to a stop. And DARPA said, well, we're going to take a break. You got 15 minutes, and we'll be back from our break. You know, they were very kind, you know. So the team went running down, and we're looking, and we're searching through. And luckily, the NC State guys knew every wire in that vehicle. And we started going through. And we found that the fuse on the air conditioner had failed. I don't know if you can tell. It didn't blow, but it actually melted up near the end. It actually had failed. So the air conditioner had failed, and the equipment had basically baked. It was like 1,000 degrees in that truck, and everything was heat soaked, you know, and it was. So next screen. So the duct tape, and we just started taping, and DARPA's going, you gotta come, we gotta start, and they were able to get things back going. And if I remember right, there was another failure. There was a battery problem or something. They got it running like at the last second. We went down and actually finished the course and got accepted to California. So I always tell the college students when we're working with them, I said, you don't give up until it's over, because the crowd, most of the people there, even some of my staff guys were going, you know, it's over. We're never going to make it now. You know, this is a terrible tragedy. And they hung in there. They kept working and working and working, and DARPA's yelling, you know, gotta go. And they pulled it together, and, you know, it paid off many times over. It was really good. Here's some of the base crew. So there's Terramax. They were the largest vehicle at the challenge. And here was us. And we actually met up with them, and because both of us had concerns. They were concerned that they were going to look right over us and had the potential for running over us. And likewise, I was concerned that we weren't going to see between their tires, and we're actually going to pull in like underneath them. So we actually spent an hour driving around and comparing notes and stuff one afternoon. And it turned out that both of us saw each other, so it wasn't a problem, but it was certainly a concern. I think I know who would have won that contest.
The second race, they had to cut their cab in half because it was too low for one of the obstructions.
One of the tunnels, yeah, they couldn't get through the tunnel.
So in retrospect, with 2020 hindsight, would you have used the Lotus if you were doing it again?
Probably. It was either that or our Suburban, which, you know, was, but we didn't have any money, and they were offering us a vehicle. It was definitely not the ultimate solution, but for a free vehicle, and everybody loved the Lotus, you know, all the college kids wanted to ride in it.
You think you got more?
They offered you a lot more than just the car.
Yeah.
They give you all
They
that
did give
support.
more.
Oh, they gave us a lot more than,
Yeah.
they were
Yeah.
very generous and
got a lot of
really
perks.
good to work with, so.
And I don't remember you talking about ever having replaced any body panels.
No,
No,
we
we
didn't.
didn't have to.
We didn't hit anything. Next. Just a couple of quick ones. Lotus at the event, they brought 3 Lotuses. This is an Exige, and then there's the next slide has 2 more Lotuses. Next one. And they brought them and drove them around. Kind of publicity for them. They got a lot of attention having all the Lotuses around and stuff. But I will tell you that Carnegie Mellon and Stanford were in our pits a number of times the couple of days before the race, and they were very concerned about how well we were doing and what was going on, and what a challenge it was to them. So I got to know those guys pretty good. They kept coming by just to chat.
I remember you getting an interview from somebody, and you said, and they said, "Why did you bring the Lotus?" And you said, "Well, it is a race."
The one Exige was, I shouldn't say this, I guess. They got stopped going like 120, near the racetrack. They were testing something, so I was like, whatever. Okay, next. So that Lotus actually supplied a mechanic who was responsible for Lotus USA. He was like the guy that if the Lotus dealership couldn't fix it, they'd call him in. Well, he actually went out to the race with us, and he monitored the car and checked it, made sure everything was just so. So it was really nice to have that level of support. So there's our final configuration. We ended up stacking the Mac Minis vertically so we could get to all the jacks. We had the power. We had all the serial to Ethernet converters there. This is the GPS INS right here, mounted right there. So
how many amps, how many watts, you're pulling all those computers, did you ever get like how much actual heat you were generating at one point?
No, I don't know, to be honest with you. All I know is it was hot and we needed more cold. So.
Did you ever look at heat pipes? Or consider them?
No, I don't remember. They considered a lot of stuff. They tried a lot of stuff. It wasn't my primary focus. I was worried about a lot of software stuff. So it was kind of like.
You gave Lotus that, I think.
Yeah, well, NC State did a lot, and so I kind of sent them off. You got to fix this, and.
Was that a real license plate on the back of it?
Yes, it was.
Mm-hmm.
Yeah, because we drove it on the road.
How did it do on its safety inspection?
Yeah, I got that before. I got the license plate before.
First, and we tore it up.
Then you had a year.
It wasn't an NC, it was a Michigan.
Yeah, a couple students had to go pick it up.
Safe.
Before we got that clamshell to put it in, 2 students had to go up to Michigan and drive it back, so. Yeah.
They really hated that.
Yeah.
Yeah. So this first clip, this was our 5-minute video that we sent in as part of the initial step in the process.
This got you into the DARPA challenge?
This is one of, this is the step before the site visit.
So you did a lot of work before that.
Yeah.
Oh, yeah.
Yeah. So.
Wow.
What was top speed you hit?
We
held
held the record at VIR, Virginia International Speedway, for an unmanned vehicle at, it was about 55 miles an hour. I forget the exact number, but. And at 55 miles an hour, that plywood base on the top started floating. The guys were like holding their hands out the window trying to keep it down. So, but it would drive 50-55 under computer control.
How did that compare to some of the other vehicles?
How accurate?
No, how did that compare?
Oh, speed-wise?
Yeah.
We were faster than most, although Stanford, after the race, really hit it big time, and they were like really blowing us away, you know. So,
Okay.
but at the time we were doing it, we were probably one of the faster ones.
In this video, is this perception driving on lines and cones, or is this GPS driving?
The way it works is that we plugged in the course, which basically has GPS description of the highway system. And then it drives, it tries to center itself on the lane, but it uses all the peripheral sensors to look for obstacles and uses the obstacles to help adjust its position as well.
So it's not looking at the lines?
It is.
Or is it-
No, it's not looking at the lines.
Well, it uses them, right? The visual stuff takes it into consideration, but not on
Well,
this
not
one.
on this one.
But in the race. it
If
did.
you're in a lane and there's a left-hand line, it will use that line to help define the lane. But in this case, it was just driving basically waypoints and using the cones as reference.
And avoiding obstacles,
Yeah.
because if you did the waypoints, you would go through those cars that are parked in the lanes.
With the computer vision, were you using OpenCV or a different library?
I believe that most of that was done from scratch.
Okay.
One of the guys on my team has a PhD in computer vision processing.
That would do it.
And he was doing his kind of his own thing, so. Here's another. This one is kind of a set of clips that show some of the different capabilities that we were required to perform as part of the Urban Challenge.
Stop sign, and we're going to go down off the pad and stop. This is another T intersection. We're going to take a right turn. Blinkers are on already, and then we're going to shoot straight out this runway segment.
Is your vehicle automatic or standard transmission?
It was automatic. Yeah, I had enough to worry about without trying to shift it. So this segment, we were required to pull into a parking space, back out, and leave. So you can't see it very well. They wouldn't let us put cones on this part of the runway because technically it was an active part of the runway.
So it's looking at lines at that point? How does it know where the parking space is?
Again, it's part of the description in the road network map. Yeah. And they actually tell you park in number 5. And so you have to go find slot 5, pull in, and then back out. See, there's a parked car, there's a chase vehicle. So he stops, he waits, hoping the vehicle will move. It didn't, so he's just going to go around.
Where's the horn function? Where's the blast on the horn? Have to put that on.
Everybody wanted to know at the intersection, how do you handle at the intersection?
Drive around.
Okay, so this is, we're going to stop at the stop line. Now we're going to go down this dead end, and we're going to get to the end and figure out that there's no place to go. So the vehicle is autonomously going to turn itself around and return on the same segment.
So did it use color sensing to tell that the road had ended and there was grass?
Well, Actually, there's a road map
Yeah.
that describes it. The different points on the map are checkpoints. And so what we get is a list of, go to checkpoint 5, 11, 22, 3, 6. And we had to calculate the route required in order to hit those checkpoints in that order. So we actually did a mapping algorithm to figure out where to go. And then once you cross the checkpoint, you got to go to the next checkpoint. So there's a checkpoint halfway up that dead-end road. So once you pass the checkpoint, you start figuring out, okay, I passed the checkpoint, now I got to turn around to get to the next one.
The one car already went.
One went, so he's waiting, and now he's going to go.
It was a weird car, the first one.
Little van.
It had little bitty wheels on it.
And what was the accuracy of the GPS you're using on the map?
2 centimeters.
Yeah, one of them was 10 or 20 centimeters or something.
I mean,
Yeah.
is that?
The backup one.
It's the
was-
military grade ones.
Yeah.
They're pretty
I
accurate.
mean,
Yeah.
I don't think civilian GPSs are anywhere close to
No.
that.
No. So,
They scramble the time signal so that you can't be all that accurate.
Drop that back down.
yeah, I'm gonna do that next.
One sensor is also a little more pricey than the other.
So that's kind of what happened. We ended up in the Urban Challenge, and I said a little earlier there was a lot of hard feelings about DARPA and how it was handled. DARPA said that they would take 20 vehicles to the finals. The night before the finals, we were in 19th place. And there was a big press announcement, and they had the press in. They decided to take 12 vehicles to the finals. So the night, we made it through all the cuts at the finals up to the night before, and then they cut us before the finals.
They
So,
changed the rules.
yeah, kind of made up
They
the
cheated.
rules. So,
Did they give any
Did they ever
reason?
announce a reason why?
no.
No.
Well, I think they were worried
Their,
about.
Capricious.
their prerogative.
Yeah.
Yeah, got breaches.
Yeah, they'll do. I think the official statement was something to the effect of safety and.
How much?
I forgot about the switches.
How much time was it going to take? Did they save any time by cutting the number of entrants?
No, I don't think it was a time issue. It was a safety concern. I guess it wasn't. They didn't tell. They didn't come
That's what they
say.
said.
Maybe they didn't think they'd learn any more from 19 or 2
Yeah,
as they would from
I don't
12.
know what their
Yeah.
their thought process was, but it
Yeah,
was.
y'all had performed better than some of the cars that were let through,
Yeah,
in your opinion,
my opinion, but.
and some
you
others
know,
too.
Yeah, so, but that's the way it goes, so.
So you
but
ended up
I-
getting all the way out there? You were saying that Carnegie Mellon was dropping by and...
We were at the finals, and we did 4 days of preliminaries and passed all the preliminaries, and then the night before the final, they cut the last. And they cut teams all the way through. I mean, every day there were cuts, and we made it through all the cuts except the last one.
Yeah, that night, we went to dinner, we thought we were in because we weren't caught.
Yeah,
And that we knew there were only 20 teams left.
and we were 19, so we were,
And that-
and then they come in and said, nah,
We'll only do
So they didn't even give you the opportunity to run the course?
no, no. So,
Well, you practiced on the course.
yes, yeah.
Yeah, we ran it in the.
We drove parts of it, not the entire thing, but,
Where was the course?
the course was on a retired military base in California, Victorville, and, it was actually, it was kind of eerie. There was houses that had been used for combat or urban training, so all the windows were gone and stuff. But there were streets and curbs and stop signs and houses and garages and.
Is that the one the Mythbusters drives around in every now and then?
Could be.
I don't know.
It's just north of Riverside.
May I ask, did the team stick together after that? What'd you guys do?
We tried to stick together for a while, but to be honest, everybody was. It had taken about 5 years of most of our all available time, and the team kind of wanted to stay together, but there wasn't a lot of impetus to make that happen. So it kind of fell apart after that.
Was there any clear path after that anyway to take it? I mean, was there another DARPA challenge,
No.
or was there
So there wasn't anything. We looked at trying to pull together, make a company out of it, but I'm a better engineer than a business person, and trying to raise that. You need a lot of capital to do that stuff, and so it didn't work out. So we all kind of went off and did some other things. But that's a great lead into my next topic, because I'd like to do another big project. I like these big projects, and I'd like to propose to this group that we get together and create a humanoid robot. Next. So what's my ultimate goal? My ultimate goal is to create a robot that the average person can't tell if it's a human or a robot.
You wanted to pass the Turing test.
Essentially, yes. It's one of the aspects of it.
That's harder than the Turing test.
Yeah. So that's kind of my ultimate goal. Now, don't get scared away, because everybody I talk to goes, "That's really hard." Yeah, I got it. So next. So I want the robot to be able to interact with natural language. I want to be able to talk to it, have it talk back to me. I want to have a reasonable conversation with it. I want to be able to tell it stuff, and when I come back, have it recognize me and remember, oh yeah, you have 2 kids, and how are your boys doing, and remember stuff, just like a real person does.
Or supposed to.
What?
Or is supposed to.
Yeah, they're supposed to. From an IEEE perspective, I think this is a wonderful opportunity to take it to the schools, to take it out to the public, and show what engineers do. The DARPA Challenge, we had so much support from the community. It was unbelievable. One Friday night, one school asked if they could come see us do one of our tests. And we said, sure, And they said, can we bring some friends? And we said, sure. By the time we got there that Friday night, there was somewhere almost 400 people at our test facility. They wanted to see the car and show the kids the car and stuff. A wonderful opportunity. I think this project has equal chance to capture the imagination of the general public, to bring them in and to let them know that IEEE is here and we're working together to what's the tagline?
Advancing technology for humanity.
There we go. The tagline for IEEE. Because of all the legal and otherwise complicated issues, if we open source the hardware and the software, we're all going to work to put it together, and then everybody has equal opportunity to take it and do with it what they want. So you're all working together to create something, and you all have equal opportunity to take that and expand on it or use it as you wish. And it's a great chance to engage our members, and that's you guys. And it's a way for the new people to learn new skills, and for the older people the more experienced people to take a role and to help lead and develop certain aspects of this project. This project has so many very technical components that all have to come together to make this work. Specifically, I want to work on the intelligence. That's kind of my thing. But to do that work, I need all this other stuff. And most companies and most startups don't have the resource and probably can't get the resource unless you're a Google and you buy 7 robot companies in a week. Most people can't afford to, put this amount of effort and resource into a single project. So by taking all this together, people can learn new skills, a great chance to network and meet other people in our community, our technical community. We have the opportunity to bring in technical experts from all over the world. IEEE, we have connections worldwide. Some of the brightest technology minds in the world. We can bring them here and have them give talks, have them help us, help work with us. So we have all those resources available to us. So why this group? Why did I come here? I've been working on this concept for over 2 years now. And why am I here? One, where can I go in the United States and pull together this level of technical expertise in a Monday night meeting, Very few places I can go that I have not only the technical skills, but the breadth of technical experience. I mean, power, we got robotics, we've got, all kinds of stuff. And everybody's here, so we can pull all those skills together. You'd be amazed that in the last however many years I've been doing this, how many people come to me and say, I'd like to do a robot project, what do you think? Should I build, what should I do? What should I do? Here's a chance to participate on something that's technically complicated that rolls into something that's much larger, and you can actually do something that, other than just for the sake of building something, we can actually come out with a working, demonstratable thing. We got technical support groups. We've got the Embed group. We've got the Linux users groups here. There's a lot of stuff going on in the triangle that we can draw from. The local universities, the School of Textiles is here. I'm thinking facial texture, So we got a lot of universities that can help us. We got technology companies with money, that we can draw on. Again, the project exceeds the capacity of most startups, and that's, to take this on is huge. And you will, if you study this or you go research this, you'll find that a lot of universities are working on a lot of the pieces, but nobody's pulling it all together, and except for Japan. And the DARPA Robot Challenge, I'm sure many of you know, was just before Christmas in Florida. And they were actually, the challenge was for a biped robot, a stand-up walking robot, to do a series of technical challenges, like drive a golf cart and climb a ladder and stuff. The winner of that was from Japan.
Yeah.
It was also a company that Google bought just before the contest. So Google's like sucking up all these companies. But Japan is doing a tremendous amount of work in this field. Biped robots, social robots. We need to get it going here. We need to get things going. If we can create an environment where there's a lot of research, recognized research going on in this area, most of us can get jobs. Who'd like a job doing robotics, So one of my goals is to inspire, develop in the RTV community, to make us an area that's known for robotics, to get the Googles to come here and see what's going on, and to get Boston Dynamics involved, and to get companies involved that recognize the skills that we have.
What if we get purchased by Google?
So what will it look like? I want it to look like a typical person. And that's kind of like whatever that is.
You're entering the uncanny region where a lot of people are discussing.
You mean like data?
Yeah. Yep. I want a very human face. I want it to look like a person. I want to build a couple of units, and I can explain that later. Next.
For mating? How better to get more?
Yeah, I can see where this one's going to go.
Build robot DNA.
So what will it do? Number one, I want it to interact using natural language. I want to be able to talk to it, have it talk to me. I want to be able to exchange with it. I want it to be able to recognize who's involved in the conversation. When I walk up to it, I want it to recognize me and be able to draw information so that the conversation is relevant to things about me and about our previous discussions with the robot. Yes?
Okay, here's one big question I have.
Okay.
Have you thought about funding?
I'll get to that. Yes, I have. Yep.
When you say a robot, are you talking head only, shoulders up, torso, full body, bipedal, standing?
I have a couple slides on that. And the question is, are we talking ultimate or are we talking... There's an ultimate goal that I want to target. It's like the Grand Challenge. When I started, I had no clue how hard it was going to be to make the car drive on the road. When I started, it was like, well, how hard can that be, you know? And 5 years later, it was a struggle. And this is the same way, but you got to have the end goal. Now, we're not going to get there, you know, the first few months or anything. So we're going to gear it down, and we're going to start, and we're going to keep. And it's a function of how much interest and how much people want to work on it. If we get a lot of people, we can dole the tasks out and we can grow it rapidly, or we can work slowly. I got a few more slides. We can come back to this when, you know, as I get done.
Is the important part here the social intelligence or the fact that it's humanoid? Could you potentially have similar social intelligence but on a different physical platform?
Sure. It's the culmination of a bunch of technologies, of which any pieces of them can be used in different places in different ways. So it's a matter of, most of the technologies that I'll talk about aren't things that haven't been done. I mean, pull out your smartphone, you can talk to Siri and have a discussion. I mean, you can do that. You can. My laptop will log me in based on my facial picture, you know, so you got facial recognition. So a lot of this stuff is done. The problem is pulling it all together and having it interact and work together in order to perform the tasks that we want to do.
Liz, isn't there an artificial intelligence aspect of it that you're thinking about?
Yeah.
So
Yeah,
that
that's what we're
every
talking
robot
about.
will be different.
Yeah,
based
that's
on
coming
its-
up. That's the
okay.
next slide. Go back. I don't think I finished. Yeah, and be able to remember previous conversations. So I want to be able to draw on the discussion, store that in a way that it can be found and used in future conversations. So I want to be able to take, and it's not only the voice. I mean, we got the visual pictures, we got the sounds, we've got the voice, you know. All that stuff's got to be pulled together, stored, such that you can find it and use it in future conversations.
Bring up the best possible ad.
Okay.
Next. Okay. The goal of the intelligence part is I want to teach the robot how to learn, not how to respond. This is not going to be, I say, how's the weather? You say, it's fine. I say, it's not pre-programmed. The programming that I want to accomplish is how do I dissect the information that was provided to me, store it, tie it to the visual imagery that's around, such that I can use that information to form verbal statements that make sense. So it's kind of a fine line, but to me it's important that it's not pre-programmed to respond to certain statements. It's programmed to learn how to acquire information and how to use English to give that information back. And if we do that, it has the weird consequence that every robot will be unique. Even though we create the same code, the robot's knowledge will be based on the people it interacts with, the places that it's been, the things that it does. So if I have robot 1, 2, and 3 and put them in 3 different places, they will basically learn 3 different things. Next. So there's several major areas that we need to focus on. The head is one. The head, we have vision, hearing, speech, facial expression. Facial expression's probably one of the hardest parts here, and there's a lot of people in Japan that are working on creating lifelike faces, and they have, I just read one has 142 actuators in the face in order to try to handle all the expressions. I want it to have normal head motion and movement, So it has a neck, it's going to have, a range of motion, so the head, in relation to the shoulders, and a real face. Next. Now the body, I perceive that there's 3 major phases to getting things going. The first one is basically a desktop model. That's the shoulders up. It sits on the desk and you can walk up to it and talk to it and stuff. We'll hide all the electronics in the body and in the shoulder area. As we get people and time and money, we go to basically a rolling platform with a full scale body. But basically it would be wheeled, would drive around and be able to maneuver autonomously around people. And then the third phase, the ultimate is a walking biped that actually has 2 legs and walks around and emulates a full person. Next. I see, in my mind, this section is like low on the list, unless we have a lot of people or somebody that wants to focus on this. Arms and hands is extremely complicated.
Yeah, I mean, the head, there's no problem at all with that.
I thought it was 45, but that's no
We could do the head. We could do the head. Arms and hands are very difficult.
But how do you get speech with hands?
You gotta have it. So,
talking hands.
But we all know.
Yeah, we can drop the head and just go with the hands.
Just go with the hands. So, this is on the list. would certainly be integrated into the system at some point. Initially, I'm focused on head, shoulders, and mobility, not necessarily hands and arms. Because I'm really focused on a social robot. I want it to talk to people. I want it to interchange with people. I don't necessarily want it to go to the refrigerator and get you your beer, you know, and stuff like that. So, you know.
A lot of people working on that project.
How about shaking?
Or maybe that's what I need to get this thing
Probably lost half
going.
the room now.
Yeah, I know. That was probably a bad
Sipping some
thing to
coffee
say.
with me.
Well, drive home
That's-
safely.
Everyone I talk to, this is really hard. Do you know how hard that is? Yes, I do. I realize that. Japan's working on it, and they're making great progress. In contrast, Europe is working on autonomous vehicles. Europe is light years ahead of the US in autonomous vehicles. Japan is into social robots and into that type of stuff. What have we got? We've got Big Dog, you know, that
Industrial robot.
and Baxter. So, so we got a couple things, but I think the U.S. we can do a lot more, and I think that's what I want to focus on. And we can succeed by using a well-coordinated incremental design process. That's how we did the Grand Challenge. It worked really well for me. We set very short-term, simple goals, and we just keep growing. And things that I thought were going to be a problem never turned out to be a problem, and things that I never thought of turned out to be huge problems. So instead of trying to solve the big picture, I am much more into, let's get something working and then start improving. Let's add this feature, let's add this, let's add this, let's grow this. And if you have a good architecture in place, you can start adding all these features as people are available and as people want to work on them, and you can grow this thing in a very organized way. No, that's okay. So basically, I think there's three or four primary teams, and how we break them up and configure them is based on the amount of interest and who wants to participate. And if it's one or two people, then you're not going to break it up. So these are kind of the things that need to be done. And how we configure them is really based on the level of interest that we get. So this is the hardware for the head, which includes the head, the body, power distribution, cabling, integration, all the hardware stuff. We're going to need people to build and do hardware. We need all the actuators to make things move and make the jaw move and the eyes move.
Are you going to be building custom servo motors?
Not necessarily.
Okay.
You want to?
If you want to, you can.
Okay.
Okay.
They're actually, talking about motors, there's a fairly new motor out there called the Dynamotor, I think it is.
Dynamatrix.
And what it does is it has a feedback. So if you connect two of them and you move one, the other one moves.
Oh.
So you can go back and forth. It's very, very good for something where, like if you have a hand that can pick up something, you can actually have two hands, and you take one and move it, and the other one moves, does the exact same thing. It's very, very good for this type of thing, because it actually, I think, works on I2E, or...
It has a serial.
Yeah, it has
control.
a serial interface to it, to the motor. But they're really, look them up, they're actually they're expensive though.
Yeah, they're more powerful than your normal RC servos.
Yeah.
They actually just had if it's the one you're thinking of, they just had a significant price drop about a month ago.
Oh, really?
And is it the Korean outfit? Is that what you're thinking of?
I'm not sure. They were, for a very basic model, was about $50 a motor.
Yeah, that's the one. They
There's
just dropped.
two competing companies.
Yeah, there's a Korean outfit that
do basically the same thing.
that does the same thing, and they just open sourced the whole design. And I think the price just dropped to about maybe $12, $15 somewhere in there. Because there's a humanoid robot that we were looking at trying to actually build. We priced it out. It was going to cost about $1,200. So we said, well, maybe not. But with this new set of motors, we'd probably do it for probably about $250.
I think the idea of sharing the hardware and the software open source makes a lot of sense. I think it's a really academic, inspired concept. But it seems like we're not taking advantage of the work that's already been done. There's been a number of robot receptionist projects around the world. And as I listen to this, really, I think robot receptionists, put it on a PR2 or something like that, right? I would just encourage reaching out and taking advantage of the work that's already been done. Would build a car if we were starting a DARPA Grand Challenge today. Use a platform that exists.
Okay.
Speaking of which, have you heard of roboticopenplatform.org? It's a list of about 5 or 7 robotic projects that are open source, including 2 quasi-personal robots. I believe they're wheel-based, most of them, but relevant to what you're talking about.
Okay, yep. It's all possibilities. It depends on the interest and what people want to work on and where you want to start. You know, it's all those are certainly options. Next. Me? From a software perspective, you've got the overall robot control. So there's going to be coordination between a lot of the major areas in the robot. The robot intelligence engine, we got vision, we got audio capture and decode versus voice to text and text to voice. But not only is there voice, but I want to be able to recognize, oh, that's the door closing, oh, that's a car going by, oh, that's a helicopter, or there's noises that aren't voice that we need to be able to capture and catalog as well. Head control and then autonomy when we get to the point of having a mobile platform. Next. Then there's the non-engineering functions that you can't do a project this size without, and there's scheduling, there's managing the open source stuff, publicity, websites, you know, speakers, all kind of. Now, and we can get people that like to do that stuff. So I'm not saying that, you know, you have to bite the bullet to do it, but we have to have that stuff in order to make this kind of fly. So, but there's management schools at the universities, and there's even an IEEE management society. So there's places we can get that, but that's stuff that has to be considered when doing a project of this size. Next. So I'm thinking basically there's 3 architects that work with me to kind of do the architectural layout stuff. And then the teams underneath all get together and help produce the different pieces. So we kind of talked about the ultimate goals and having, you know, but what's realistic? And my kind of stake in the ground is in 1 year to have a unit that we can demonstrate to students and groups. And that's kind of wishy-washy. I mean, that could be really fancy, or it could be, you know, real simple. But basically a desktop model, no arms or body, get the facial stuff working, get the voice working. So that's kind of what I'm thinking is realistic in a year, is to get the basic stuff working. And then we have the opportunity to grow and expand and to add on to it and to make it bigger. Now when we talk about budget, I think to get started that we can get some money through the local organizations to get started. Now the question is, I don't know how much we need, I don't know how many people are going to participate, and I need to pull all that together to go forward. But if we come up with a reasonable demo that shows that we're working together, we're making progress, conceptually what we're doing makes sense, there's a lot of opportunities for significantly more money. Not only by getting sponsors outside of IEEE, but IEEE Foundation has money for projects like this, particularly if we're doing it for STEM and for students and for the growth of the IEEE members. There's money that can be found. So I don't have a good answer to that, and unfortunately it kind of depends on the number of people and the participation and how things kind of roll out. Initially, we'll probably be a little thin, but if we can get things going, I think that potentially there's a lot of money to follow up and to improve and to make it better. So. One more, I think. Oh, yeah, required commitment. A lot of people that I've talked to have said, well, I don't know, I'm real busy, I'd like to, but in my mind, this is a good news, bad news story. We have no deadline. If it takes us 2 years to do it, if it takes us 3 years to do it, that's what it takes. If we get a ton of people that want to do it and we're off and rolling, then the schedule comes in and we do it. So it's really based on what you as the members want to do for this project. And we have the capability, if we have a lot of people, to move, shift around. You know, if one group is behind, we can add people to it and move around. So the good news is there's no deadline. We can work at the rate that the participants are willing to work at. The bad news is it's easy for things to kind of fall apart. You know, people, well, I can't do it this week, I'll do it next week, and things kind of, so we will have some artificial deadlines, and just to keep the project moving and to kind of keep things rolling, we'll kind of set some. But they're adjustable, they're arbitrary. It's not like, you know, we have to be ready for a certain event, or we have to, you know, demo this on a certain day. It's really whatever the members want to do with it, how much they want to participate, and how much they want to work on it. Last one. So, in my mind, what's next? One is I need to know kind of who's interested and what you're interested in. So I can kind of see, do we have enough people to kind of make this fly? Right now, this is simply a proposal that I put together. If there's not a lot of interest, then that's okay. If there's a lot of interest, then we need to organize it. We need to figure out what teams we're going to put together and how we're going to make this thing fly. So that's an email that you can send to me if you're interested. If you kind of tell me what you want to do and kind of your skill level. And if you're a newbie, I think that's wonderful. We'll match you up with some people that have some experience. If you're experienced in a certain field, I need to know that, because I'm going to have to draw on some of you to help solve certain aspects of this problem, because it's huge, and I understand that. But there's a lot of very interesting pieces in here. I mean, there's voice, there's vision, there's motor control, and a lot of software, coordination, there's intelligence software. So there's a lot of stuff to be done, and we can pull together and work on this if there's interest. So I'll open the floor to